Hey, it's Mr. Stoletano. This video is going to be on metals, nonmetals, and metalloids. So at this point we know that to the left of the periodic table are the metals, right? And then we have like a staircase going right here that tends to separate them from the nonmetals. What we may not have talked about is that the staircase is actually the metalloids, which we'll get to in a little bit. But the first thing I wanted to address, this is a common question people have, is some of these things that you don't think of as metals outside of chemistry are metals. So for example, sodium, potassium, calcium, magnesium, things like that, people tend to say, well, don't I eat those? I don't recall ever eating metal. And you're not wrong, we do eat those, right? So for example, we have salt, right? When we ingest salt, we have sodium chloride. So what's really important to note is that when metals are in their elemental form, right, so they're not a part of any other, they're not attached to anything else, and there's no charge to them or anything, it's just a neutral element form, neutral atoms of that metal. Like sodium, for example, they're very different than when we ingest them, for example. So sodium chloride looks very different, right? It's chemically bound to chlorine, has entirely different properties. Same thing with the potassium we eat, or like the things in our vitamins and minerals that we get. Those are ions or in compound form, so they have very different properties. So you're never going to have it be like, man, I tasted the metal with that one. Very different properties, right? So this is actually what sodium actually looks like. So pure elemental sodium, nothing else attached, not an ion, just a neutral sodium atoms. It looks like this. And so you can kind of see it looks like metal, right? We've got kind of a shine going there. So that's one important point to point out. So let's take a look at just a reminder of where these things are, and this video is going to talk about what makes them really different from each other. Some of the things you kind of already know, and some of them a little bit of a review. So here's our sort of our locations, right? So like we said, pretty much everything to the left of our staircase are the metals except for hydrogen. Hydrogen's an exception, a special case. Hydrogen's a nonmetal that happens to be over here, partly because it has one valence electron, so that's why we put it in this column. But yeah, so that's not included. Also important to note that these guys down here are also metals. So people tend to forget that these are actually included. These technically come from the belly, or the inside of the periodic table right here. So those are also included as metals. As you go to the right, though, you tend to get less metallic, kind of less metally in quality, where you have the metalloids, which are in yellow here, that are along the staircase, and those guys are kind of hybrids. They're kind of halfway between a metal and a nonmetal, which we'll talk about. And then as we continue to the right, we're in full-on nonmetal mode, where we're not metallic at all anymore in our properties. So it kind of makes sense. It's like a spectrum, where as you go from left to right, you become less metallic, and you become more non-metal-like, essentially. Okay, so let's talk about metals. So as you saw, 80% of the periodic table are metals, right? Even the things you wouldn't think of as metals. So think back to some of the things that you need to know about, some things you know about metals already. They conduct electricity, right? Something people think about less often is that they are thermal conductors. In other words, they conduct heat very well as well. When you're cooking, you're not going to use a fully metal spatula because the heat might run up and burn your hand. Maybe you use like a wooden spoon, a non-metal type thing. So yeah, they conduct heat and electricity. They have a luster, right? That's a fancy word for they have a shine to them, which we can see over here as well. So that's more of our science term for that. They have a shine, they have a luster. Malleable, which I always think of as malleable. Mallet is of course a hammer, right? So if something is malleable, it can be hammered into sheets. So non-metals, you wouldn't be able to hammer them into sheets, they would just crumble, right? Ductility is another new word. So it tends to be these three words, luster, malleable, and ductile, that people tend to have as new ones, so commit these to memory. Ductility, or something being ductile, means it can be formed into wires, which is something that we really only do with metals, right? Another thing is that most of the metals have 1, 2, or 3 valence electrons, which are loosely bound. So that makes sense. Metals 1, 2, or 3 valence electrons. Those 3 columns tend to be 1 to 3 valence electrons, and then it goes into no longer metal anymore to the right. Those electrons are loosely bound. So if you didn't realize it yet, electricity is actually electrons. And metals conduct electricity because those electrons are so loosely bound. So essentially, when electricity passes through metal, it's the metal exchanging electrons like hot potato over and over again from atom to atom through the metal, so that's why it conducts so well. It doesn't hold its electrons very tightly, and that's why it's easy to just pass that current right through it. And also, metals tend to be solid at room temperature, right? The vast majority of metals, almost all of them, will be solid at room temperature, except, what's the name of this guy? So that one is actually mercury. So mercury is a liquid at room temperature, as we know. That's the only exception, essentially, for metals. Okay. Now the other extreme, right, the upper right-hand corner of the periodic table are the nonmetals. So pretty much the opposite of what we just said, non-lustrous. In other words, dull. Not much of a shine to them. Here's sulfur, for example. Poor conductors, right? They don't conduct electricity very well. Brittle solids. So instead of being malleable, where you can hammer it into sheets, if you try hammering one of these suckers, it's just going to break into pieces. Very brittle, right? And they tend to be solids, liquids, or gases. Nonmetals can be the whole range, right? We've got oxygen gas. We've got carbon solid. Bromine is a liquid, for example. It's actually the only liquid nonmetal. So that's another kind of a fun fact there. So they can be all three things, or metals we just saw as only solids. And also, most have only 6, 7, or 8 valence electrons because they're at the right-hand side of the periodic table. And those valence electrons are tightly bound, so this is all related. They don't conduct electricity very well because they hold onto their electrons so tightly. You can't exactly pass electricity, which is electrons, through a substance if it won't pass them on, if it just kind of gets stuck there. So because of that, we tend to call them insulators, right? They don't conduct electricity, instead they insulate, they stop electricity in its tracks. So that's for the nonmetals, essentially. Metalloids, so this is the hybrid, right? Metalloids are like, they're along the staircase, they're in the middle on the spectrum between metals and nonmetals. They have kind of properties in between both. So one of the biggest things, for example, is that they conduct electricity relatively well. Not as well as metals, and certainly better than nonmetals. So because of that, we use these for our semiconductors. So we use these for our computer chips and things like that. Things that we want to be able to conduct, but not to like a really high extent. Just a reasonable extent to work on our electronics. So that's essentially it for the properties of metals, nonmetals, and metalloids. Thanks for watching. Remember, chemistry is everywhere.